Okay, I think that is just about everyone this morning. So thank you all for joining us again today. It's good that so many of you could join us for both sessions. Let me just start by sharing my screen. Wales confirmed that he can hear me, but if anyone's having problems with audio, please let me know. I will try and fiddle from my end. Mark, is that yes, you're having problems with audio, or yes, you can hear me? Okay, that's what I'm going to share. So just to start us off, I'll just do a quick review of what we covered yesterday. So to start off yesterday, we discussed the performance model of modern processor architectures and discussed some of the contrast between CPUs and graphics processing units, and talked about some of the considerations about how we program them. And we discussed around their programming abstraction and how HIP and CUDA programming model allow us to deal with have a host and a device, transferring of data between them, and how we now need to start considering this memory management in more detail, whereas often when we have CPU-only systems, our compiler is dealing with a lot of the memory movement for us. We then discussed how we do this explicitly through the APIs. We did an example on there. Then just before lunch, we looked at how you execute a kernel. We ran through an exercise of just doing a multiplication of a vector, which built on our memory management example. After lunch, we then discussed some performance considerations if you end up with how thread indices and block indices run, and if you've got multi-dimensional data, or you try and describe your data in a multi-dimensional way, how you need to order your threads in order to access the memory independently, and therefore take most advantage of all the vast number of threads in a graphics processing unit in order to get the benefit from the system. One moment. Right, sorry about that. We then, in the afternoon, discussed, after dealing with these performance considerations and looking at a matrix example, we then moved on to looking at managed memory, and then I handed over to Juan at this point, and he discussed shared memory and constant memory. And we looked at some synchronization and some issues with how we do reductions. So today, we're going to talk about, I'm going to talk about two things in the morning, up until the 11 o'clock break, and then I'm going to hand back over to Juan to finish off the day. So firstly, we're going to talk about streams. These are very important for making sure you drive occupancy if you've got multiple different work and you want them to execute at the same time, because you may want to have multiple things happening at the same time on your different threads. And then graphs, which allow us to try to combine sets of operations into some form of structure, and that allows us to then execute them together, and helps to sort of reduce some of the overhead costs if we've got lots of individual kernel calls. Okay. That's not what I wanted to do. I wanted to do this. So, streams is the first thing we will cover this morning. So, really what this is talking about in terms of streams is you have the concept of independent branches of action. So far, when we've executed a kernel or a memory copy, these operations have implicitly been submitted to the default stream. Okay, This is associated with the current GPU context that we're working in. They're submitted to the same stream in serial, and they're executed in order they entered the stream. There is a further opportunity to overlap independent operations here and manage independent streams of different asynchronous work. Okay, so if you've not got the ability to use all the threads in one particular kernel called of the GPU, but there is something else you were going to want to do next, which is entirely independent, putting them both in different streams and then executing both of the streams will get this work to run potentially at the same time or overlap slightly. And this will mean that you get a increased utilization, better occupancy of your GPU, and therefore potentially fast time to solution. Okay, so stream management is relatively simple. You have a stream object which is declared using hipstream_t, and then you need to initialize this via the API called hipstream_create. And then when we're done, we release the stream by calling hipstream_destroy on that stream. Okay, so think of a stream as a resource. I'm going to allocate a resource, and I'm going to free the resource later. And we can create an arbitrary number of streams. That may not be sensible to do. We still have got a finite amount of hardware resource that we can use, but we can think about trying to organize our operations so that the independent things can have the potential to overlap. It's up to the scheduler that the GPU is doing for this asynchronous work to decide when things happen. But if you've given it options, it will be able to run things hopefully simultaneously. Okay, so we have talked about, you could think about this in terms of kernel executions, but you could also have an asynchronous version of memory copy. So this is called hit memory copy async. It takes an argument stream at the end, which tells you which stream this memory copy is going to execute in. If the final stream argument is omitted, it takes the default stream instead. The thing to know here, this is the same as your standard hit mem copy, unlike hit mem prefetch that was sort of mentioned yesterday, and it requires both the destination and the source memory references in order to operate. But the point is that you can set this up to run, and you're saying at some point, please do this operation in this stream when it gets to the right point in the stream, and you can issue these operations to the stream in order, and sometime later they will happen. Okay, and if we've done this, we need a way to synchronize, because we need to know when these things are completed. So to synchronize on a stream, you have hipstream synchronize, and that says that we now can assume everything up until this point in the stream has completed. We can then start issuing to the stream again, but at that point I know I've got a certain amount of work done. So if we need to kick off a bunch of streams to do some work, at some point I need to know that that set of operations is completed, and I can do something else before I kick off my next bunch of work. Then this is how we guarantee that we have completed everything that's currently queued up in the stream. Okay. So that's memory movement in streams. What about kernels? So we also have the same type of syntax for submitting to a non-default stream. But this time we have an additional argument, but it comes into the kernel, these sort of angle brackets submission form. We've got an additional argument here, shared size t. We're just going to set that to 0, so that it's just a because the positions of the arguments, we just need to give it some value here. So you'll see it come up, but we're not going to touch that right now. And we provide a particular stream object to the kernel, And if you don't like the this angle bracket notation, you want to use the full form of the kernel launch, it's just an additional argument on the end. Okay. We also have the concept of page locked or pinned memory. So HIP provides a mechanism to control allocations made on the host. This can be beneficial because what you're doing is saying in a normal memory copy, it's having to move to the data to a page location and then move it onto the device. Instead, when we malloc the host memory, if we put this in a pageable location or page lock location, then this extra copy doesn't have to be made. There's potential performance benefit from doing this. This is very simple. We just have a new function we call for malloc, but this is now HIP host malloc. And again, we provide a host pointer that's going to be for this memory location and a size. So this just replaces our malloc calls that we've had before. So this allows HIP to supervise allocations and do optimizations in transfers from host to device as well. So the reason this is important here is if we're really starting to care about performance, that we're starting to put things in separate streams and trying to get them to overlap and synchronize, then we're going to probably start to worry about our memory copies and the time it's taking to do that if we've got a lot of asynchronous work all happening concurrently. Whereas before we had a pattern where we'd move a large chunk of data, do a load of operations, then move it back. Here we're talking about trying to keep everything on the host for as long as possible, and then if we're really trying to keep data there and minimize movement, when we are doing movement, we probably don't want that movement to be efficient. So there's an opportunity for optimization here that you could be aware of as well. And the only other thing to say here is to release this, you can't just call free or delete on the pointer, you now need to call HIP free host. Yeah, and as it says here, these allocations are often used in conjunction with streams where efficiency is paramount concern. Okay, so that's a very quick overview of the concept of streams. You have independent pipelines of allocation. I think there was a question yesterday that asked about whether this was possible. This is the mechanism for doing it. So we're going to jump right into an exercise now for probably 20 minutes or so. And in this case, we've got a revised. We're going to revisit the previous BLAS call that we looked at yesterday. DAG. There is a new template supplied for this exercise. And this is just aimed to illustrate the use of streams and page-locked host memory. So the suggested procedure is for vectors X and Y. You can replace the relevant HIP mem copy with an asynchronous operation and try to use two different streams for each of the mem copies. Because these are just moving data from host to device, they can happen at the same time if there's capacity to do that in the system. So therefore, you may gain a performance benefit because you're not serializing the memory movement. So this is a very simple thing to overlap. It's not going to necessarily have a huge amount of benefit because you're not necessarily spending a lot of time waiting around for this. But ROC-Prof, you can profile this, and because these are now independent, you should be able to see some overlapping. There's this tool called Perfecto. This is kind of recommended from AMD about visualizing ROC-Prof output. I don't want to distract too much by going into the details of that, but it's a way to visualize locally via a web browser. If you want to do that, you can download your profiling files and upload them here. I think it's just a JSON file that you need for this, and you'll be able to see some timelines with that. Yeah, so the check you can replace the host allocation with the hip host malloc, and make sure you adjust to free the results at the end. And then the bit that's kind of got cut off here, I think, but is kind of implicit, is that the kernel you're going to execute is going to be executing in a stream as well. So you're going to need to think about synchronizing. If you're doing a copying in two different streams, you're going to need to know that both of those have completed moving data to the host before you then before you then execute the kernel. So you'll need some form of synchronization step in the middle of the stream. Okay. So let's try this exercise for the next 20 minutes. Will we go over the solutions for 204 and 206? So those were. Yes, okay. I think there are solutions that are available. I'll try to look at that and make sure, see if we can get to have a look at that after break. Okay, while people are looking at this exercise, I will have a think about how the best way to put that in is. So just on that question in chat, the answer, so the question was around, does HIP malloc managed the allocator which manages memory between host and device? Page lock the memory is used, and the answer is it depends on what it can access. So reading down that page a little further, actually, it suggests that if certain Linux functionality is available to it, it will try to. If not, it will just fall back to system memory. I think it will probably try and make some optimization choice if there's a limitation on how much it can page. So it will probably keep things it's using quickly and moving back and forth there. And this is kind of the real point, I think, is that that managed memory says go HIP, go and do something sensible, and whether it does that or not is not always clear. And whether it starts moving stuff back and forth between host and device quite frequently may impact your performance, even if it is correct. So this mechanism just described with HIP host malloc gives you more control. Yes, there's another question around, would you recommend managed memory for quick prototyping and then page lock memory and multiple streams for optimization after things are working? Yes, get a working system first and then optimize. You are going to get memory moved around by HIP, the HIP runtime managing your memory. That's going to be suboptimal. And by doing the management yourself, there's potential performance improvement, but only put that effort in if you see this as a dominant effect. That's what I'm looking for. There are example solutions for these. I will talk through this one in particular. But if you look in section, let me just get this right, send you all the link. So you're just passing it in as d_x. Same as you would do for same as you would for standard host device copy. But are you freeing or are you destroying? Let me just get this right, because the syntax is hip stream destroy, not free. You'll need to, yeah, if you've added the stream into the kernel, then as well, the stream still needs to exist. So as part of the release resources part. Yeah, is that syntax? Yes, it is. It can be the same stream you pass to your kernel. So the point here is that the question asks you to try and generate two streams so that you can overlap or get the copying of data to overlap. Then the kernel can be run, but it has to run after that data is moved over, because you need X and Y on the device before the kernel can execute. You then can use one of the streams to run the kernel call, but you must have synchronized before it. Once the kernel has used the stream to run on, then you can destroy both of the streams. Sorry, do we need device synchronize if we've got stream synchronization? I'm trying to think how that hierarchy works. I think if you call device synchronize, then stream synchronize within that. Yeah, so device synchronize waits on all the streams. So we can have two kernel calls, one for each stream, as long as they're synced. Yes, it would be good to capture them in the Etherpad. You're quite right. Let me try to do that. Actually, Juan, are you able to try and copy some of these questions over to the Etherpad?
Yes, yeah, I did that.
Okay. Okay, performance-wise, so Relic Kevin, I'll come back to yours in a second. Performance-wise, is using only one of your streams at a time the same as using the default stream for the same task? Yeah, the default stream is just it is what we fall back to. If you only use one stream, you've got no opportunity for running multiple streams at the same time, getting concurrency, so then you might as well have used the default one. So Kevin asks, so we can have two kernel cores, one for each stream, as long as it is synced. Yes, so in this example, you don't need to call the kernel twice because you're doing one operation. But if you did have a case where you had two kernel calls, they could, and they're independent work, they can run in different streams, and they can potentially run on the device at the same time. And then what you're doing is you're saying to the HIP runtime, I've got this set of work, it's independent, you choose how to schedule this efficiently. And what you're really looking at is that if you are struggling to drive occupancy, you're giving the GPU more work to do. So it should be able to better utilize all the threads it's got. And therefore, you're going to get better performance through the system. That's the idea. Kieran had asked, could you run the kernel on the default stream as long as the other two have just synchronized, haven't been synchronized? Yes, that should be fine. You then effectively have three streams in play, but that's okay. The point is that when you really come to use this, you really want to say, I've lined up a little pipeline of work that's going to starts to depend on each other, and that will come on to what we're just about to speak to. Now, the default stream always exists. Okay, I'm a little bit wary of time because the next lecture is going to make this a little bit more complex again. But for that example, but the important thing I think to say is that for these examples, and I think I'm just going to paste this in the chat, there are example solutions for these problems, and these are getting to the more complicated end of the examples. So I'm preempting a little bit, so please don't look ahead, but if you do want somewhere to look at potential solutions, sorry, I just need to find the exact bit I was looking for. The lookup key here you can use. Okay, so for those that are getting a bit, so there's a couple of solutions there for some things at the end of yesterday, and there's an example of this stream solution. This doesn't, I think the only problem is I just realized this particular solution here doesn't use 2 streams, but I will show you a version of that right now. Just try and clarify this a little bit. And obviously we'll come to look at the graph section next, so don't look ahead of that just right now. Okay, we've spent a little bit of time on that. I'm aware that people are probably still thinking about it, but if I will look at a solution now, because I want to show you some of the plotting that what this looks like with some of the graphing tools that are available as well, because it may help to clarify some things. So, yeah. Yeah, streams aren't really directly related to stream processors. Stream processors are a piece of hardware. Streams in this context are like a pipeline of work. The work will end up being executed on a compute unit which contains stream processors, but they are not somehow linked. Okay. So, right. Okay. So this is the example we're going to look at. We've got some kernel. That is what we've been looking at up until now. It's the example of doing this, forming this matrix out of 2 vectors and scaling with alpha. We're not doing anything by default. We've got our normal host pointers that we've set to null. We've got some device pointers set to null. We are probing our usual device properties. Nothing has changed here, and we're checking if we have a GPU. If we don't have a GPU, we stop. Okay, so now what we're going to do is we're not going to allocate host pointers like we were before. So these bits have been commented out with this these double arrays. We're going to manage that separately now. What we're going to do is we are going to first set up some streams. I'm going to call one stream A and one stream B. I am then going to create stream A and stream B so that they are available to me for the rest of this section of the program. I am then going to do my allocations now with these vectors hx and hy as hip host malloc. Okay, I'm providing them as I before to an address to where this pointer is that we originally set to null, and it's going to fill it with an address of where this host memory is. I am going to keep HA as the same. I'm going to keep this as a this is just a return value. I'm only ever having this on the host, and I'm copying back to the host. I'm never copying to the device of this HA. I'm then going to assert that these all exist to make sure everything's fine, and I'm going to fill the host versions of X and Y with some dummy values. So just 0 to minus their length. Okay, same as we've done before, nothing's changed here. Right. I'm then going to do my usual thing of allocating space on the device to take copies of the X and Y vectors and my matrix I'm forming on the device. This is where we do the new thing with the synchronous copy. So I'm now saying that stream A is going to take care of the mem copy async X, and stream B is going to take care of the mem copy async for Y. It's two different streams. They can do these potentially overlapping. It's probably not going to be a huge benefit in this case, but if I had very large copies or I had lots of them and they could sort of do this at the same time, then I'm going to get benefit from overlapping work. I'm then going to synchronize these to make sure that both of these copies have completed before I move forward. So I make sure both streams are ready and done. Okay, and I do that before I then call my kernel. Okay, I'm going to call my kernel on stream A, but as I pointed out, now I've done the synchronization. I know the data is there. There's nothing that's really stopping me from calling this on the default stream. The solution, the example solution that I've just provided a link to in the chat, just does this all with a single stream. It doesn't try to do the two. And the point there, it just sets up a pipeline that you have to do a copy, another copy, and then you can do call the kernel and then synchronize between. Okay, the structure's the same. I move data. I have to guarantee the data is on the device before I can operate on it. Therefore, I have to synchronize. Then I can do execute my kernel to do my operation, and then I'm going to call, as someone pointed out in the chat, I don't need to assert afterwards on particular streams because hip device synchronize is going to make sure it waits on all streams to make sure everything's completed before I move forward. Okay. So my work is done. I'm going to copy back as I've done in my previous version of this. I'm going to hit mem copy from device to host, and then I test my result to make sure it's correct. Okay, and then the final thing I need to do is I need to free my device memory, and I need to destroy my two streams, and then free the host malloc memory, the pinned memory. I now have to call hip free on opposed to delete because hip's going to sort out to make sure that's removed correctly for me. Okay, that works. And then I'm going to show an example of what this profiling thing looks like. So let me just actually not jump around there. So when you run the profiler, you get given a JSON file out. And it's giving you a bunch of data about what the operations are happening and so on and so forth. And this is pretty much not very readable around the trace of events that are happening. In order to make this a little bit more being able to process this, then you have this Perfecto tool that AMD have linked on their webpage, and I've just loaded in this JSON results in here, and I am able to scroll through it. So let me just get to the starting point. And what I could start to look at is, when I expand all the elements, and start to zoom in sections and see that there's particular calls to various functions I've got. Okay, so I'm going to create some queue. I've got my hip streams created here. That's being called. It's taking some time to set this up, so there's a bit of a cost here. I've got another hip stream create. So setting up the concept of streams is taking me some time, and I can start to pull out where things are happening. So I've got my kernel launch, I've got my mem sets, and I can start to look at, in terms of timing, about what's taking the most time in my operations, and start to see where I might get overlap. I can't pull out anything obvious here at the moment, but you can just see that in a sort of timeline view, you can start to identify where certain things are being done, and you can see my streams getting destroyed at the end. So the point here is I have some stream create, some other stream create. I do my operations. Here's some hip mallocs. If I really zoom in, I'm going to do some memory asynchronous copies. Another one's here. I'm taking quite a lot of time to do some mem setting. My kernel launch is taking a little bit of time. And then I've got to do my device synchronize, where I wait for all my streams to synchronize. And then I'm going to do my mem copy back. And finally, I just clean up and destroy and do my hip freeze. Okay. So the point of this is this tool might help you understand a bit better around what's happening in terms of all this asynchronous work that you can't necessarily determine what order is happening in because you're letting the runtime do that. But you can start to use the output from the profiler and stuff to sort of program. Okay. I have got slightly behind here on my schedule. So I'm going to discuss hip graph launching in a second after I just answer a question. And then once I finish that talk, I will take a break. And then we will look at the exercise. Okay. Right, the question is the memory free on host memory meant to be host free? Have I made a mistake? There is always the chance of that. And they will have done. Sake there. Let me just check. There may be that the API is going to save me somehow. What? Can't see anything off the top of my head. I may well have just made an error there. Apologies. Thank you for catching that. Okay. So, before we move on to talk about graphs, is there anything else people wish to be clarified around streams, or does that help to make things a little bit clearer? How I call kernel, okay. So I have my kernel, do my usual thing of providing blocks and threads. I just have a 0 in here because there is a shared memory amount I can put in, which just needs a value placed in it. For now, we're not doing anything with that, so it's just set to 0. I pass a particular stream here to the kernel itself. What happened to stream B is I've synchronized on it. It's now sat idle in the background. It's not doing any more work. And later, down at the bottom, it is destroyed. This is a dummy variable. Sorry, this is a bit of a dummy example, right? I could have, at this point, stream B doing some other useful work. So what you could do is you could say, let's say you could call this twice, but the problem here is that you would need to guarantee that you were working on different data or a different copy of the data remotely. Otherwise, two streams of work are going to try and operate on the same memory locations. So I couldn't pass in dx, dy, and dA into a second my kernel call running on the stream B, because then I'd be trying to do work on the same thing and I get some form of race condition, and that would be bad. So I need to be careful about that. Okay. Okay, that said, I'd say this is probably one of the more complex sort of topics to get your head around in terms of this. Streams and then graphs are kind of we're really trying to push for performance. So if this isn't quite clicking on the first time we're reading through, that's okay. It's really to make sure you're aware of them and having an opportunity to experience what they do. Try the exercises, but there is a solution available if it gets a bit confusing. So streams provide a mechanism to control execution of independent or asynchronous work with a more general mechanism than just the streams, okay? This idea is that now I can put some form of dependencies between pieces of work. And I can build up some form of graph of these. So you can use these to orchestrate complex workflows, and it may be particularly useful of amortizing the overhead of many small kernel launches. So what you want to do to make sure that your GPU has high occupancy, to make sure that it is efficient or is being utilized heavily. If you're unable to do that because you don't have just a single very large piece of data to operate on that's going to chunk through with blocks and threads and just keep working on that until it's got through everything. Instead, you've got lots of smaller things to do. Ideally, you want to write your program in a parallel way that allows it to stream through a lot of work. Instead, if you find yourself running lots of small kernels to do different things, you can use graphs to try and reduce the launch cost of each of the small kernels. So this takes an idea from graph theory. You have it to represent individual execution items of work as the nodes of a graph, and the dependencies between them as the edges, these connecting arrows, connecting the nodes, okay? And what this does is gives you the ability to describe each of your works and what the dependent pieces need to use. There is an assumption here that there is a beginning and an end, so there's a direction to these graphs, and there's no closed loops in the graph picture. That said, there's a very recent development from the CUDA developers that they've now started to look at loops inside these graph structures a little bit as well. It's not something that the HIP API will have for now. It's just more of a comment to say that this is only just starting to be considered. It's breaking this condition. But for the majority of the examples we'll be looking at, and for the majority of code that exists today, there is no sort of looping. You have to have a direction, and this is where this concept of directives, acyclic graph, or DAG, comes from. Okay, you might hear this terminology. The idea is then you construct a description of the graph from constituent nodes and the dependencies, and then execute the whole graph in one go. And then the runtime can make decisions about its dependencies and where it needs to keep things, and where at what level in the GPUs and the caches it can maybe just leave something around its execution. Then you're going to get some efficiency and performance. We're going to leave most of that up to the runtime, but if you declare that there's a dependency, it can then make decisions based on those dependencies itself. Okay, so creating a graph. So we have an overall container for a graph of type HIP-T-graph. Is allocated in an empty state it's allocated in an empty state by the API function HIP-graph-create. We just pass 0 into the flags here, so we literally just make it and then we create it. So the typical life cycle of a graph looks something like the stream, but these are different concepts. I have my graph, I make the object, I create the graph, I then destroy the graph. Okay. So the destroying the graph will also release any component nodes and dependencies within them. So that's the structure of the graph as well gets released. So the graph is a container that owns the objects you register with it. Okay. So having created a graph object, one needs to add nodes and dependencies to it. Once this has been done, we'll show adding nodes in the discussion below. One creates an executable graph object. So we create a graph, we add objects to the graph, and then we launch it, and we destroy the executor of the graph, then we destroy the graph itself. Okay. So we have a graph executor, and we instantiate that graph executor with a particular graph it's going to run, and then we can launch it into a given stream. So here you see I have this nested approach. I can have kernels that make up members of a graph, and I can launch all the members of a graph in a particular stream. And then I can have multiple different graphs being executed on multiple different streams at the same time. So I can get a very complicated pattern of work going on, but the fundamentals are the stream allows parallel types of work to be going on at the same time, as long as they're independent. That's up to you, the programmer, to make sure they're independent. And the graph allows you to combine kernels and memory movement into some structure to make sure that all the dependencies are worked out inside there. So you create a graph, you instantiate it with its elements, you build an executor, you instantiate the executor, you launch the executor, and then you destroy the executor when it's done, and then you destroy the graph. Okay. The idea here is that the instantiation step performs a lot of the overheads of setting up the launch parameters and so forth for a bunch of smaller kernels, and therefore you're going to save cost on the setup phase of launching of the smaller kernels independently. That's the idea, and this can save you a amount of time and therefore gain performance. And this again is where looking at this graph, that sort of timeline plot I just showed, where you can start to see these effects if they're lots of small kernel launches are adding up and seeming to be quite a large percentage of your time. You can start to identify that and maybe start to move groups of things into graphs themselves. Okay, so that's the overall structure. So the graph definition. So what we talked about is instantiation of a graph and instantiation of executor and a launch of it. We have different node types. They represent a number of different types of operations. So valid choices are things like mem copies, mem set operations, a kernel call, but also a CPU function call. Okay, you can have these in your graphs also. So specifying a node of a graph means providing the description of the argument in which you would have used in a normal invocation, such as we've seen with mem copy or with the kernels itself. We need to know things like blocks and threads and things like that, and the arguments you're passing to your kernel. They need to be provided to the graph so it knows what to call when it's going to execute a particular node. So first node we're going to think about is the kernel node. So assume we have some kernel function, my kernel. It takes a double A and a array X. Its execution configuration includes blocks and threads, as we've seen with all our other calls to the kernel functions. These parameters are described by HIP. Described in HIP by a structure called HIP kernel node parameters. Okay, and this has a number of public members. So I need to provide a pointer to the kernel function itself. I need to provide the list of arguments that the kernel is expecting to take. I need to provide the number of blocks. So this is the size of the total grid of work we're going to pass in. and I need to provide the dimensions of the block. So that's the number of threads per block. Remember, these are these grids of blocks are three-dimensional. That's listing three things. So we're just going to think of a simplified one-dimensional case here. But you can see how this can get rather complicated if I've got three-dimensional data and I'm passing this around. So what does this actually look like to do this in practice? So here, just below as an example, so I have one of these objects, HIP kernel node parameters k params. I'm going to initialize it with a value of 0. I'm then going to have a list of my kernel arguments, which are going to be addresses of these particular values. And I'm going to pass these into k params, which is going to describe the elements, the arguments that my kernel needs to launch. So first of all, I've already pointed to my kernel itself, the kernel parameters that we just stored in arguments, the number of blocks, and the number of threads per block. Then we've defined all the elements of a particular node, and now we need to add it to a graph. So we're going to do that by defining a graph node, and then a graph add kernel node. We pass in k node, which is our kernel node, to my graph, and we pass null and 0 here, which we're just not going to worry about right now, and then we pass in the parameters. This null and 0 relate to dependencies. At the moment, we're just assuming we've got no dependencies. We're just going to execute. We're going to add this one, so I'm going to add, not execute, add this kernel in to a graph via its node and with its parameters. So this creates a new kernel node and adds it to the existing graph and returns a handle to the node. Okay, and the handle to the node is now k node. So I can basically keep a list of all my nodes, and I've got a list of all. I can separately have all their parameters, and I construct graphs out of these items. The formal description of this adding graph add kernel node function is described here. So I have the node, I have the graph, I have some dependencies, I have the size of my dependencies, or number of dependencies, and then I have my parameters. Yeah, and this is if the new node is not dependent on any of the other nodes, then the third and fourth arguments, the null and 0 I just mentioned, are there because there's no dependencies, and the number of those dependencies is 0. Okay, what if we have now a memcopy node? We have a similar procedure to provide memcopy, but this is a little bit more involved because there's a bit more we can do around memory movement and to express all the details of memcopy. So these structures have so we have the following function: hip memcopy 3D params. Same as before, the params we have parameters we have the kernel. It's very similar. We've just got a few more items we've got to fill in. So stuff we've seen. So we've got the destination position and the pointer to the destination. We've got the extent, number of blocks that we've got for this particular pointer, piece of memory. That's what I'm trying to say. We've got the type, the kind of the copy, the direction of copies, host to device, device to host, and we've got the source position and the source pointer. So again, we've got destination information, an extent, we've got the kind of copy, and we've got a source. So while there seems like a lot here, actually, they're all the items that we've used before when we've dealt with memory moving between host and device. So this is rather involved because it must allow for the generality of copying, allow all the copying allowed by the HIP API. So let's make this a little bit more concrete. Let's just consider an explicit HIP memcopy operation. Okay, we have a device pointer, that's our destination, a host pointer, which is our source. We have the size of the data moving, and we have the kind of movement we're going to do, hip memcopy from host to device. So as in a similar way we did with the kernel parameters, we now have a HIP graph node. I'm just going to call this node for our new graph node, and we're going to have a HIP memcopy 3D params and params for our parameters. We have some helper function here to fill in all the information. Of the kind of obvious, we know that's just one-to-one mapping this HIP memcopy host to device. We can figure out the extent. So this is three-dimensional. We're saying the extent, the first dimension is this number of data elements times the size of double. This is all just a single-dimensional array that we're going to copy. And the start position of this is at 0, 0, 0. And we pass it the host pointer and size and the number of data elements into source pointer. And we do something similar for the destination pointer. The position is going to be at 0, and we pass this helper function, make HIP pitch to pointer, provide some data to set this up. And that's all the information we need for the parameters for setting up any given memory movement in HIP, in a graph. And again, we need to add the HIP graph, add this information to the graph itself. So this is our node. We're adding it to this graph. We now have a dependency. We now say we're going to be dependent on the kernel. So we've got one dependency, and then we're going to pass in all the parameters. So we've made it dependent on the preceding kernel. So this is just this graph is very simple. It has two nodes and one link. So the data structures for this are documented more on the docs. The link is provided. This is quite complex to get your head around. It took me a couple of readings through to remind myself exactly what's going on. So do take time to think about this problem and in some detail. So the final thing we need to discuss is synchronization. So if we're executing a graph in a particular stream, we can just use HIP stream synchronize to say that we have ensured all the elements of the graph have completed. It's also possible to use HIP device synchronize, as we discussed earlier. This synchronizes on all streams running on concurrently on the device. Okay, so what you're guaranteeing is that your graph has come to an end using any of these methods on that particular stream. Okay, I've overrun slightly by 5 minutes because we had a quite useful discussion around streams earlier. This is a bit of an involved example. If this feels quite complicated, I've given a list of where you can see a solution for this in section 6.01. Have a look at that and try to write a simple example. So we're going to use the same matrix construction example as before. So see if you can replace the single kernel launch with an execution of a graph. There's a new template provided. You won't really see any performance improvement associated with this because we haven't got enough nodes executing to see it or amortize the cost of the number of kernel launches. But this exercise is more about trying to understand the principles of having a graph inside, set up in the runtime, and what this takes to set up the information for this. If you manage to get to the end of that, then have a look at adding device to host memcopy with a dependent operation. Okay. But these also take some time now to have a break also. So given that, let's plan to restart at 11:30. I probably have completely destroyed our plan schedule at this point.
That's fine. I think 11:30 is right to start.
Okay, so there is, yeah, so we're okay if we.
I mean, we also have the lunch break that it will be.
Let's restart at 11:30 as planned, and I will try to be quick at explaining the result of this. So it's important to state that there's some time. So the final exercise this afternoon, looking at the conjugate gradient algorithm, this is meant to be a larger problem, an algorithmic type problem that gives me an opportunity to use some of these tools in a wider setting. And there's some examples provided to help you look at each of the individual elements of that problem. So there'll be an opportunity for some time to review this material in another context as well, if you don't feel like you've fully got it this problem. Okay, thank you for the feedback, Mark.
James, I'm aware that you need to leave earlier. If I mean, we can do the break shorter. If I mean.
Okay. So we're just going to take a few minutes before lunch to look at the graph example solution now, and then we will take an hour off between 12 and 1, and we will return, and Juan will take this afternoon and look at the section on device management, and then the final part of the day before running up to 3 o'clock when we'll finish today is going to be on a more complicated example. It's not more complicated in terms of the tools we've used for the HIP API, but in terms of trying to pull together some of the BLAS operations we've been writing in the various examples into a simple conjugate gradient algorithm. The idea is to try and combine multiple parts of this together. So, see John's rejoining. People are leaving. Okay, I'm going to move forward with this now. Hopefully everyone is here if you wanted to see this. I'm going to do this on the light screen simply for speed, and this is the example solution. So we have a standard example that we've been looking at. We have our kernel function, and a little bit bigger. That we've been looking at up to now. We're going to update the matrix A using the vectors x and y. We have our main functions, and this is some rectangular matrix. We have our usual definition of a bunch of host pointers, and device pointers, and our scaling factor alpha. We do our device property checks that we've done lots of times before. Nothing's changed here. Checking we've got a GPU. This time we're not doing anything special with HIP host memory or anything. So we've got our usual allocation of arrays on the host, just using an array of doubles for HX and HY, and we're asserting they exist. We're going to fill them with some values that are just very much related to their size. And then we're going to allocate some memory on the device. So this is our dx, dy, and dA. So this is based on the size again, just so we've got our destination for copies of our initial values. We set a type of the kind of where we're going to do the copy of this data, and then we move HX and HY over to the device, and we set to 0 the matrix A on the that's not what I wanted to do, on the device. So now this is the bit where we have the graph execution going on. So it's in this little scope. We have a HIP graph which we initially set to 0, and we have a HIP executor that we initially set to 0, and then we're just going to create the graph. We're going to create the executor later. We do our usual thing with our launch parameters. So we've not changed any of the way we're blocking this. It's just the same it's been for several of the examples in terms of divisions, two-dimensional blocking. We've got a 2D number of threads per block, and we've got that's the same. Okay. So in this, we've already done our movement of data onto the GPU without using the graph. So we're going to do two things here. One, we're going to set up the graph to execute the kernel, and then move the result back, and that's going to make the total of our graph. So we have a graph node called knode, initialize it to 0, and we need its parameters to set up this node. This is k-params. And then we list all the arguments we're going to pass to the kernel. So we need the size of the row, the size of the column, alpha, this factor we're going to multiply by, the device pointers to the x and y vectors that we're going to use to generate the device matrix ADA. We're going to pass this then into this k-params parameters helper structure. So we're going to pass my kernel, we're going to pass the arguments, we're going to pass the blocks, and we're going to pass the threads per block. We're then going to insert this node, knode, into the graph, called graph, with this call. And we're going to pass the parameters in here. Remember, the null and the 0 represent that there is no dependencies at the moment. That's the null, and the 0 says that the number of dependencies is 0. Then want to think about copying the result of this kernel call back from device to the host, as we've done before. We're doing basically the same operation as we've always done. There's nothing actually changing in terms of the work we're doing. We're just changing the way we're describing the work to the HIP runtime. So in this case, we now need a second graph node. We need HIP graph node t called mnode, initialized to 0, and we need a HIP memcopy 3D params per m params. So in this case, we've got the kind of memcopy this is going to be is device to host. Its extent is going to be rows times columns because we want the full matrix times the size of the double. This is going to be flat array, so it's only got one dimension, so the other dimensions are set to 1. And we start at 0. So that's the source position. And then the pointer itself is the sources on the device, so that's d_a, and then we find size for this. We then have the destination, we do the same, but this is now HA, the result comes back our matrix on the host, and we provide similar information there. We now need to add this new data, this memory copy node to the graph. So we've got explicit HIP graph add memory copy node to the graph. And you can see now, well, before we didn't have any dependencies, we have one. We're saying my new node is going to be added to the same graph as before. It's dependent on the previous node, the kernel node, executing and completing. Otherwise, we won't have done the work to get the right results. So you need to make sure that's completed before you run this particular node. So there's one dependency, and I am passing in the parameters I've just set. Now we've defined our graph, we can instantiate the executor of the graph executor that we just initialized to 0 earlier. And then we can launch it. And once it's launched and run, so in this case, we're launching it into the default stream because we're not passing a particular stream parameter in it, we're just passing null in here. Once we've completed the launch and that everything's run in the graph, we're going to use HIP device synchronize on this line to make sure that all the work is complete and all the streams have finished everything they're doing right now. So this is the default stream that we care about in this particular case. And then we need to clean up after ourselves. We need to call HIP graph the executor and destroy the executor. And then we need to destroy the graph itself. So what you can see here is you could end up with patterns where you have the same graph being executed in multiple places. So you might want to keep up with the graph you've built, but then generate and destroy executors for that graph at later times, or have the same executor and launch it multiple times. So you can build up complex graphs as and when you need for your particular application purposes. Will the graph destruction destroy the device memory? I think it just destroys, let's check. I think it just destroys the graphs, but unless we've got an explicit free below. No, we're explicitly having to free the device memory, so I don't think it does. It will destroy the member nodes explicitly though, because all we've provided the graph nodes with is pointers to where the memory is. I suppose that's enough to do the destruction. But you could want that to, you wouldn't want that to be default behavior, because you may want to get the result of a graph execution and that remain present on the device for something future. So if you destroyed your graph and then delete all the data, then that may not be very good for you. Okay. Hopefully that's helped to clarify that the graphs are an option to you when you're designing algorithms to run on GPUs. Kind of the aim of them is to try and reduce the cost of kernel launches if you have lots of small kernels, and allow you to explicitly write in dependencies. The key point here is that this example isn't doing anything different to what we've seen before, and it's really trying to just give you another framework. Give an example of another one of the ways you can launch work on the GPUs that are available to you that control dependencies explicitly, and try doing the same way, do something, the same thing in a different way that we've already seen. Okay, that's all I had for this morning. Thank you very much. So I just answered Mark's question before we go. So graph as an infrastructure could host access that pointed to the device A later. Yes, until it's freed, it should still be there, and you could then copy back to another location later. Yeah, with a mem copy, exactly. I'm sure there is a flag that allows you to destroy everything, but I'm pretty sure default behavior means that it lives until you explicitly destroy d_a. I'm not going to every element of the flags that you can possibly put in, but that's the default. Okay, that's lunch. When we return at 1 o'clock, Juan is going to be taking you through device management and how you start to think about having more than one device. Just a little bit of an overview about how they can talk to each other. And then finally, we'll finish off with the conjugate gradient example. But that's all for me for now. Please post any questions you have in the Etherpad, and we'll try and look at them after lunch. Thank you very much.